In this video I will show you how you can do joint hypothesis testing using the Wald statistic. Before we get to the Wald statistic, let's quickly do a recap of the T statistic. The T statistic is equal to x bar minus mu over s over square root of n, and is approximately student t distributed with n minus 1 degrees of freedom. Okay. This means that our measured mean minus our assumed mean over the measured standard deviation over the square root of the number of observations I have. And I can do this test for mu is greater or equal to some value, less than or equal to some value, and exactly equal to some value. Now the Wald statistic looks a little bit different. The Wald statistic looks as follows. R times theta minus R prime, R v hat over n, R prime to the minus 1, and R theta minus R. And this one is approximately chi squared distributed with q degrees of freedom. This looks much more complicated, but it's actually still relatively similar. Okay, let's try a simple example and see how this Wald statistic looks and if it is different from this T statistic. Let's assume the following. Let's assume we want to test the hypothesis, so H naught, that, let's say, mu is equal to 5. If we want to test this hypothesis, we have a mean minus 5 over s over square root of n up here. And for this Wald test, or Wald statistic, what we get is the following. In this case, this term here is equivalent to the term up here. Our theta is our estimated variable. In this case, x bar. So what we get is r equals 1, theta is x bar, r is 5. The middle term is 1 times v hat, which is a variance covariance matrix, or in this case s squared over n times 1 again, inverse, or divided by it. Well, this is the same as the top part. This part here is the same as the bottom part squared. And then we have the top part again. So overall, this term is just this T statistic squared. And we know that if a variable is normally distributed, if we square the variable, it will have a chi-square distribution. So, okay, these two are reasonably similar from variable tests. How about if I want to adjoin test with two variables? Well, one way to do that is I test it separately for the first variable and then for the second variable, and I get two T statistics. I can test both of them and either reject or not reject these hypotheses. There's a problem with that. What if I reject one but not the other? Would they jointly be rejected or not? It could be that one is slightly rejected and the other one is very much accepted, and together they would actually still be accepted. The Wald statistic allows us to test that. Similarly, it could be that there is a high correlation between the two variables we're testing. If there is a high correlation between the two variables, positive or negative, we could improve the efficiency or the preciseness of our estimate by taking this covariance into account. So we would get a better result or more accurate result using the Wald statistic than this t-test. Okay, so now we know why we might want to do a Wald test, even though it looks much more complicated. How do we actually do it? Let's assume we have two variables. One is test scores, and the second one is distance to school. We ask the same students, and so we can get a potential relationship between the two. It might be that students living further away from school have higher grades or have lower grades. I will assume a negative correlation between these two variables, but that doesn't have to be actually true. Okay. Let's assume there's 64 students. Their average test score is equal to 81. And I want to test, is that significantly different from 80? And the standard deviation I get is 4. Y bar, the distance from school, is 5 miles or kilometers. Epsilon, which I want to test, let's say that's 4. They both happen to have the same side. So my mu is lower than x bar and my epsilon is lower than y bar, but in reality that does not have to be the case. And I have a standard deviation of 1. As I said, I wanted to have a negative correlation between the two, so let's say the covariance is equal to -3 for simplicity. Okay. Now that I have these two variables, I can do these tests. I could do these tests with the T statistic, as I said before. I just have two tests and I test them separately, but I wouldn't take into account this covariance. So taking into account this covariance, I might get a more precise estimate with this Wald statistic. So how do we get that? So what is R, what is theta, and what is little r? Well, big R here, or let me write this as a system of equations. Let me write this as a system of equations, which makes our life much easier. So let's call this top one x bar minus mu is equal to 0, and y bar minus epsilon is equal to 0. I have a system of two equations that both are equal to 0, and I need to get the same format here. Well, if I want the same format, then I get R equals the identity matrix. Theta equals x bar, y bar, and R is equal to mu and epsilon. If I multiply theta times this R matrix, and I subtract this R, I get exactly these two equations. X bar times 1 is x bar, y bar times 0 is 0, minus R minus mu. So the top line is x bar minus mu, and the bottom bar, by similar construction, is y bar minus epsilon. Okay, now I have all these. This means I have R, I have theta, I have little r, oh, and v hat. And I have is 64, right? Okay. What is v hat? Well, v hat is our variance covariance matrix. I have two standard deviations and the covariance, so I can easily construct it as 16 minus 3 minus 3 and 1. So this is my nice covariance matrix, and I have all the terms in here. Now I need to do some crunching of the numbers to actually get what the value of this Wald statistic is, and then I can compare it to the chi-squared distribution with q degrees of freedom. Now what is this q? This q is the number of equations that I test simultaneously. So in this case, I test two equations. And because I test two equations, I have a q equals 2. Now, this is not really a very interesting case. because assume this covariance is 0, or I'm not that interested in this efficiency, I could still test these two hypotheses separately with this T statistic. Also, this Wald test for this kind of hypothesis test is slightly more restrictive than the T statistic, because the Wald test can only test equality hypothesis. The T test can also do greater or equal or less than or equal. But there are specific cases where I only can use the Wald test. For example, I could test if the sum of these two estimated means has a specific value. This is not possible with the t test, but is possible with this Wald statistic. Well, if I do that, I need to change some of the values here. And for simplicity, let's assume that I want to test if the sum of these two means is equal to 85. It actually is 86, but I want to test is that significantly different from 85 or not. Okay, the variance-covariance matrix is the same. My theta, well, I still have x bar and y bar. No difference. What changes is my capital R and my little r. Okay, so let's set up the equation quickly. So I want to test x bar plus y bar minus 85 equals 0. That's my hypothesis, and I want to test this one. But if I want this equation in this format here, I still have the same theta with x and y, well then my r better be 1, 1. Because if I multiply this vector times this vector, I get x bar plus y bar minus 85. So we have r equals 85, little r. And now I can multiply this according to this formula here, and it will be chi-squared distributed with one equation. Only one equation is tested, 1 degree of freedom. Thank you for watching.